So my name is Ulrich Fuchs. I'm from CERN, the European Center for Nuclear Research. And let me start by saying that I'm totally aware that the two most difficult talks are the ones right after lunch and right before a drink. And now it's the second choice. So I will try to keep it light because, I don't want you to run away. So basically, I want to go through 3 sections in this talk, tell you just 2 slides what we are and what we are doing, just because you might not be aware. What we plan to do, that's a nice crystal ball talk. And then talk about the tests, the hardware tests we're doing today. So let's start. So who are we? And what are we doing? That's the second slide. So let's start. So we are an international, European international organization, founded in '52. So now all European member states are part of CERN. We also have so-called observing states. So you see on the right, so with some exceptions, mostly in Africa, that's for budgetary reasons, all states are present at CERN with physicists. So we are about 2,000 staff, 10,000 visiting scientists that come with their equipment, families, and whatever. So we are, let's say, a little town of our own. And so in one line, our job is to study elementary particles and the fundamental forces in the universe. Sounds cool. Now, how do we do that? It's basically we are not too far from Palo Alto, so accelerator physics, as we are doing since 1958. And we built that was not what I wanted to do. We built what is today the biggest accelerator in the world. It's called LHC, the Large Hadron Collider, about a circumference of 30 miles, about, let's say, 1,000 feet underground. And we are accelerating a beam of protons or lead ions to about the highest energy we can produce on this planet reasonably. And public relations talk would be, so we are shooting a beam of 85 kilograms of TNT through a 3-millimeter hole about 10,000 times per second. Okay, so a nice toy to play around. You use these particle beams, you force them into collisions, you create a whole bunch of new particles. These you have to measure, detect, measure. It gives a lot of data. You see, this is a data storage conference after all, so we get to that. And there are 4 big experiments on that accelerator: ALICE, ATLAS, CMS, and LHCb. I'm working for ALICE. And big box. A particle detector, I don't know, Geiger counter for you, something handheld, little box. This is not that little. You see a person in comparison down here. It's not the biggest experiment at CERN, but it's the heaviest. It's about 10,000 tons. That's a bit heavier than the Eiffel Tower, which depresses the French. Any French people here? I'm sorry, in case. And by the way, it's another world record. So the red box around is an electromagnet. It's the biggest magnet in the world. So then you can continue with doors and sizes and 35,000 amps going through it, whatever. So I'm not here to tell you that. Now, what happens, this is just a nice animation. So you take 2 accelerated protons, you smash them in the middle, it's cool, destroying stuff. And you get this wonderful bubble of new particles flying in all directions. They cross all the layers. Every layer measures a different property, weight, whatever. And in the end, you take all this data together and you turn it into physics, physics into papers, papers into Nobel Prizes. That's it. So now, what do we get? Out of the accelerator, we get about 40 million collisions per second. For every collision we are interested in, we have to read all the electronic channels. There are about 100 million readout channels. That adds up. So what we expect to get is about 12, 15-ish terabytes per second, 24/7 throughout the year. If you plot one collision, it looks like this little something down there. Most of it is known stuff we don't care about. And somewhere hidden in this forest is this event. For example, that's one example we are looking at. So we have to process this data to find these tracks. We will also talk about compute in a minute. So that occupies a couple of servers. Just as a history, so because we are doing this for the last 50 years, we have a long history of computing at CERN. It's always the first version of Machine X, the first network technology X. We had the first Ethernet in Europe. We had the first TCP/IP installation in Europe. So whatever, we developed the web for various reasons. And I put this photo up there because it's so cool. Just a second. That was the delivery of the first CDC in Europe at the time. And the guy standing there was the Director General. I can tell you when I buy a server today, he doesn't come anymore to look at the box. Okay. So times changed. So yeah, you had a question.
You said it's 1 terabytes of data per second.
Yeah.
Is the memory access pattern fairly sequential? Is it random one?
Give me 10 minutes. Okay. But very good question. So now, here's the answer.
How long is the capture?
Non-stop.
Hours.
No, years. Sorry. No, we run, it's not a triggered readout, it's a continuous readout. And we run for 8 months a year. Then there's 4 months maintenance. And this for the next 20 years. Okay, so just this is a quick run through because I'm the service manager of the data acquisition group, so I show you the slide. On top, we have about 8,500 fiber links, homemade protocol that come in. They're connected by homemade PCI Express cards to about 250, 280 servers. They just do a DMA, they move the data into memory, from there we move it to the network and off it goes. So that's just box moving. They're connected to our wonderful data acquisition network. So the data drops out on the bottom. So now we have to do this little pre-compute I showed you before, which means zero suppression, data formatting, calibration, you name it. Not the real analysis. That takes months. I'm just talking about data formatting now, okay, in memory, moving pointers. And to do that, we need about 1,500 servers with 4 GPUs each. That's a 2.5 megawatt data center. Okay, just to give you an idea. When it's difficult to see, so the output of these servers, so we put 15 terabytes per second in on top. These servers, they each write to 60 to 80 megabytes per server. So the sum is about 150 gigs. That's doable. So, and this data goes hardly visible into this little can. And as I usually say, I like this in all these graphics. I mean, the storage system is more expensive and more complex than all the rest, but it's reduced to a can. And this is, okay, fine. So we move it into the can. And from there, at a certain rate, data management facility, it moves out to tier 0 storage, then to the universities. So this is where the real analysis takes place. Because up to the can, it's a real-time system. And then something bad happens. Now, you fill I have to explain you so you really appreciate the catastrophe. You fill the accelerator with particles, you accelerate them, you do your collisions, but in every collision you lose particles, of course, the ones that collide are gone. 40 million per second, wow, there are a lot of particles in it, who cares? But over 8 hours, the intensity in the accelerator goes down. And usually after 8 hours, we say it's no longer worth running the whole IT installation for recording basically nothing at the end. Let's dump the rest of the beam and refill the machine and restart. That's a procedure of about 3 hours. So that's quite an investment. If you count that in money, sitting there for 3 hours doing exactly nothing. Okay, I save on electricity, but in terms of investment, because after 5 years I have to replace it, count what it costs per hour. No. So there is the fantastic idea, okay, we have to recalibrate the data anyway, because right now you think the gas pressure is this. After 1 hour, after 10 measurements, you have a medium, you know better what the gas pressure is. So let's read the data back and recalibrate it. So, and in fact, they are quite clever. They are doing this while we are recording data, because the moment you have one collision, the particle is gone, intensity goes down, there might be a free CPU cycle. So you start reading back data. So in fact, we do it at 100% during the pause, the refill of the accelerator, but we do it already on the fly while we are recording data. Our CPUs, GPUs run at 100% load 24 hours a day. Okay, if there's a free CPU cycle, I use it. Please tell me. We use it immediately. So that's nice. So what about the CAN? So, okay, capacity about 60 to 800 petabytes, because it's just a buffer. This is not the final storage, it's just a buffer. We start writing, we start reading back, recalibrate, so the recalibrated data needs to be written, a pre-analysis. So, on the CAN, we get to about 450, 500 gigabytes per second, and now it's mixed I/O. It's no longer strictly linear. And now we're going in the direction of your question. So the input from the fibers is, of course, linear. What happens on storage is all mixed. So, okay, and then in the end, we move it off to tier 0. A word about the capacity, where the 80 petabytes come from. Everything from top up to the data management facility is in the same building. So there's not a problem. The tier 0 tape facility is 15 miles away, and the fibers cross fantastic industrial areas, etc. So the chance to have your fibers cut is very good, already been there. And when you cut the output, you have an X off all the way to the top, so basically you stop. You can no longer write the data. So the other part of these 80 petabytes, which is about 20, this is just disk buffer so that I can continue recording data even if you cut my fibers. And the rest, about 60, is cold storage, because I told you before, we stopped the accelerator after 8 months and we have 4 months maintenance. What do we do during these 4 months? Now we can do full-fledged data analysis. I cannot call the IT department and say, oh, by the way, the 300 petabyte we put on tape, could you quickly restore them? I need them tomorrow. So, no way to do that. So tape for us is really a write-only media. Okay, we will never read it back. No, we keep it on site. So just pile it up there in the corner and we will have a look at it later. So, now, let's have a quick look at the CAN. Basically, I told you all of this already free-handed. Capacity, I told you, you connect about 2,000 clients. You have a mixed workload per client, read and write mixed. Okay. You have different workloads, different things running, but you open a file, you read it linearly or write it linearly to the end, you close it. So each access is linear, but then there are many mixed ones together. The 2060 I told you already, so this is autonomy and reprocessing at the end of the year. Now, yeah, we started to have a look. Well, fine, you can call a computer vendor of your choice. Can you sell me this kind of stuff? Of course you can, and give me your bank account. So no, we started to look at different file systems. Well, there are not that many that can actually handle this amount of data and at these throughputs. So just to run through, so we looked at Lustre, GPFS, the usual 2 suspects. Of course, GPFS, rather Ceph, and there's an in-house solution, EOS, which is basically a Redis store with a HTTP access to it. So it's a homemade Dropbox, if you want. And now, can they do it? Well, we have to test. So to mention it immediately, the tests are still ongoing. This is not the final conclusion, not the final word. So we are testing linear workloads, read-write mixed, but every single workload is linear. Big files, more than 2 gig, big block sizes, more than 1 meg. I mean, I have data, I want to get rid of it as fast as possible. And yeah, it's all about throughput. So, and okay, we will come to the developments at the end. Now, test setup. Very simple. I mean, you have seen Lustre setups. You have some metadata management and then multiple object stores. So these are servers with simply disk arrays attached. I'll come back to that later. And a communication network and clients on the bottom. Okay. I mean, we are using CentOS 7 now to do that. Now, let me quickly flash these slides. That's now the starting point. That's what I presented last year. Quickly, are we doing something stupid? 1 client, 1 stream, 10 gig, internet, how much data can I get to disk? And you see that with GPFS and Lustre between 1.2 and 800, so I more or less saturate the network. Reading, more or less the same thing. Ceph Rados performed a bit less, but okay, fine, this is still acceptable. Here it gets interesting. There's already an order of magnitude. But okay, one stream, one client, fine. Okay, one client, X streams. So now let's load the client. How much can I get out of a client? I mean, the plots look surprisingly similar, but it is write and read. It's two different operations. But again, you see that basically, I have to mention something about this. So we can saturate the network. This was on InfiniBand, so we could go a bit higher. Same there. And with Rados, okay, we got about half of it. Still enough for X clients, one stream. So now let's add machines to the thing. And basically, that's the last slide of this kind of test I want to show. Here we are talking Ethernet, 40 gig Ethernet. So basically here we saturated what the network can deliver. This is a big question mark we'll talk about later. And for reading, I mean, please keep in mind, Lustre was running on InfiniBand. We hit a nice maximum of 11 gigabytes per second, whereas Rados was at 100 on the same hardware. So this triggered some investigation, as you can imagine. But okay, so this is what we've done, and I presented already last year. Now a little update to this. So GPF Lustre, we saturated the network in one case and the storage controllers, because they're the servers, SAS connection, and the disk chassis. And then RAID 6, or in this case, so RAID volumes in the disk chassis. The controllers can usually do 1.2 gigs per second. That's already not bad for a controller, but okay, in my case, not enough. There are two controllers per chassis, so one disk chassis is limited to 2.5 gigs. Okay, fine. That was tremendous 5 years ago, and today it's a bit, well. And a word on the Rados stores. So it was the Hammer distribution. Now, we checked on the disk arrays, and for 100% linear write, there was 30 to 40% read. And so, in fact, it's not a bug, it's a feature. Because you write something, and before you tell the operating system, okay, the write was successful, you read it back, you compare. So basically, even a linear workload was random on disk level. So that explains the throughput. So there was a nice plenary presentation this morning. So I'm looking forward to testing the new storage backend and rather see what that changed. For reading, let's just go back. So why can I exceed the maximum delivered by the controller? Well, very simple. We're talking RAID controllers, RAID hardware. When you write, you compute your checksums, you compute your blocks. But for reading, it's a pass-through. Unless there's an I/O error while reading, the RAID controller will not recalculate parity and do all the checks. So yes, we have a much higher bandwidth in reading than in writing, so that explains that. And we were basically limited by the network interfaces. On that topic, completely off topic, but that's the point. If your disk delivers wrong data, but not an I/O error, your whole RAID controller serves nothing. You get it. Okay? So, fine. Now, what about the network? And yes, so you have seen before, okay, we saturated the controllers in one case, but also the network links. I mean, with the GPFS, etc., we were hitting the 5 gigabytes per second, which is 40 gig Ethernet at the time. And with the InfiniBand, the 11 gig at the end, these were two servers on FDR. So 2 times 5 gigs per second. So it all fits, sort of. So let me just show this. So now these are the latest results. So we tested, now we focused on one product now, Lustre. Now, how does it perform on different network links, providing enough hardware so that the network link becomes really the bottleneck. So now here, sequential I/O by I/O zone, read-write, fine. So 2 servers on IB FDR. So yes, as I showed you before, so you peak at about 11 gigs per second for a read, and 6, 7 gigs per second for write. I mean, here it's the controller, here it's the network. No big deal. That's the cool stuff. In many storage chassis, you can enable caching. And usually it's switched on. And here you see, I mean, you have write, read for cache enabled and disabled. And in fact, disabling the cache increased the throughput. That was surprising. But in the end, no, not that much, because you use the full disk bandwidth and you don't bother moving bits around in the controller. Sequential I/O. So what was the next test? Random. So first, in general, so what's the performance we could get out of the same setup with I/O zone and random I/O? I mean, the write, as you expect, we're talking IOPS now. So that's already not, well, okay, not that as good as the reads. Easy to understand. I mean, if you know I/O zone, I mean, you're writing to files. You write, while you do it, you need a lock on the OSD, while by reading, Lustre supports partial file locks. So actually you can have multiple writes or reads to the same file, to the same OST, so data store at the same time, while for the write this is not possible. So here you block yourself, you shoot yourself in the foot while the reads basically continue. And now just the write, now random writes with and without caching. And here you see with the cache, here the cache really pays. So as a general rule, I would say leave the caching enabled. Disable it only if you really know that you have strictly linear writing workloads. Otherwise, you can get into debugging sessions that take 4 weeks. Okay, so much for FDR. Then, of course, OmniPath. So just 2 slides to stay. You have comparable statistics for everything. Read, write, okay. Now we need more disk arrays. We doubled the bandwidth compared to FDR link. So 14 to 16 gigabytes per second, and now also in write. Okay, so this is about what you can get through this network bandwidth. Right. That's about it. Random was a very surprising plot. We verified it, but nature is like this. And so basically really writing at 15,000 IOPS, we saturated. For reading, we really thought, expected, and that was a surprise. Okay, still to be understood. Now, what is missing? Ethernet 100 gig. All I can show you is a nice screenshot. These were tests. In all these tests we are 3 guys doing it. And now I'll let you guess, the other 2 are in Houston and Austin. And about 3 weeks ago, we had other priorities than doing 100 gig Ethernet tests, as you can imagine. So that will be an update maybe for next year's conference. Okay, let's call the wrap-up function. So with GPFS and Lustre, we basically could hit the limit of the storage controller and the interconnect network, providing enough hardware. So here, the protocol itself has never been the bottleneck up to now. Ceph Rados, as I said, it's a feature by design. It's made for safety. You don't lose a single bit over I don't know how many years. So it's made for safety, not speed. Future versions will improve performance. I put this sentence before seeing the presentation of this morning, so now I'm thrilled. And as I said, what we observed were the 30 to 40% read for a strictly linear write. Also, of course, related to the journaling. What about data integrity? So Lustre is based on LANs provided by the operating system and basically trusts these LANs. So it's up to you that this LAN either represents a LAN from a storage array, which is already exposing a RAID 6 or whatever group, or if you use ZFS, that this is a pool with mirroring with whatever. So, but Lustre doesn't care. It just uses the LAN. I ran Lustre on a memory file system. So by definition, nothing rated or safety. Lustre doesn't care. Throughput was nice though. GPFS does its own cluster, well, its own protection. They call it declustered write. Interesting technology if you want to read about it. And rebuild times. So, as I said, Lustre itself, you destroy a volume, it comes back. It's basically a second to resync and then the volume continues. However, how long the LAN itself needs to rebuild depends on the hardware you use behind it. And as we know, with RAID 6 and sufficient number of disks, your volume might stay in maintenance mode forever. Interesting story, I don't know if you heard that. It was a company that really bought racks and racks of disks, formatted in RAID 6, started to use it. What happens after 3 months? Disk failure, the thing rebuilds. Well, during the rebuild, another disk failure, doesn't matter, RAID 6, no problem. Let's finish the first one, kick in the second spare disk while that one rebuilds, disk failure. Anyway, after another 3 months, every single volume they had was in rebuild. The performance, of course, you imagine. And the rebuilds over the next 4 years never finished. And then they decided, okay, let's not wait for it, let's just throw it away. So, fine. Funny things. And GPFS claims that they can rebuild within their declustered rates within minutes. When I'm done with Lustre, I will redo the same exercise with GPFS, and trust me, I will try that, challenge them on that one. Network, well, yeah, now we moved from 10 gig, 40 gig headaches, etc., to 25, 50, 100. Omnipath, InfiniBand, EDR, Ethernet, etc. So we get very nice low latency links now. And basically now we move the bottleneck to the storage controllers. Yes?
Are you using all three of those or one?
Let's say for the final setup, we haven't decided yet. So I have to test all of them, which is good for you, so you get the results for all of them. Huh? And so yeah, basically we now push the bottleneck to the storage controller in the arrays. And there's a very simple solution to it. Let's remove it. And this outlook, I mean, you know these boxes. They're becoming more and more popular. In case you have never played with them, I encourage you to do that. So it's basically a 4U chassis. There are also 5U models. 90 to 100 disks in them. And in the back, you have the storage servers directly in the same chassis. They connect to the same backplane just from the other end, and they have a full SAS connection, individual SAS connection, basically to every single disk. Okay, there are also some disks on the backplane, you connect to the backplane, etc. So there are different implementations. But in any case, so you boot the server, you see 45, you see 90 disks. And now you build a software RAID, so suddenly the performance of your RAID group is limited by the CPU you have in it, and no longer by a storage controller. So you will see that on the next slide, you get much better bandwidth to RAID sets that way than with the traditional hardware controllers. Okay, there are different models, different vendors, different form factors, whatever. So the highest density I know will come towards the end of the year. It's 100 disks in 4U. So that is interesting stuff. Now, we had a first hands-on with one of the chassis. And for RAID 5 and 6, we tried both of them, groups 8 plus 2, we got 14 gigabytes per second write, 12 gigabytes per second read. Okay, with Lustre, then of course, let's say, of course, it was a bit less, 10 and 7 in 88 disks with spares and whatever. But in 4U, I mean, the results are similar to the plots I showed you before, but before it was 2 servers, 4 disk arrays per server, every disk array had a JBOD extension, etc. That was several racks. Now I can do the same thing in 4U. Just to give you the feeling, this is, there's something going on here. And I consider this a perfect solution for people that look for high densities and in this case, so cheaper disk space per rack unit. And the conclusion for me is, well, so let's forget everything I've done and redo all the measurements with these chassis now. But good news for you, no, thank you. I show you that next year because I think it's time for a drink. So, and as I said before, I would like to thank Quita and Mario Gallegos for the collaboration. And I mean, they were flooded out a couple 2 weeks ago. So this is why we don't have the internet results, but I promise next year they will be there. Okay, thank you.